Good morning, everyone. In the last lecture, we have seen some examples regarding state space representation. Let's do some more examples with this topic. Let us consider an example like ys over us is equal to 1 by s plus 2, s plus 3, s plus 4. We have the system, a transfer function, and now we have to find out state model of this transfer function. So we have options. Either we can multiply these three terms, and find a transfer function of order 3, or by using partial fraction we can write this as 1 by 2 divided by s plus 2 plus minus 1 by s plus 3 plus 1 by 2 divided by s plus 4. And after partial fraction, we have three different transfer functions, and these three are added together to form a transfer function ys over us. Means what we are doing, we are finding a transfer function by using parallel structure. Means these three transfer functions are parallelly added to form a final transfer function ys over us. If I can draw its block diagram, how can I draw? Let's see. Here we have an integrator. Here is x1, and here we have x1 dot, and from here feedback of minus 2 is there, and it is added here, right? And with this x1 I multiplied a transmittance of 1 by 2, another integrator. Here we have x2 and here x2 dot, and from here a transmittance or a feedback of minus 3 is added here, and from here I multiplied a transmittance of minus 1, and again an integrator. Here we have x3 and here x3 dot, and from this x3 a feedback path of minus 4 is added here, right? And with this x3 I have multiplied again 1 by 2. Now the outputs of these three terms are added together, and from here like this, and finally we get ys. and the inputs of these three are shorted together. Inputs are shorted together. This input is US, and this is a block diagram. And from here you can write y is equal to 1 by 2 x1 minus x2 plus 1 by 3 x3. Sorry, 1 by 2 x3. Right? And x1 dot is equal to minus 2 x1 plus u. x2 dot is equal to minus 3 x2 plus u, and x3 dot is equal to minus 4 x3 plus u. This is the state model, and in matrix form we'll get like this: x1 dot, x2 dot, x3 dot, and minus 2 0 0 0 minus 3 0 0 0 minus 4 multiplied by x1 x2 x3 plus 1 1 1 and u, and y is equal to 1 by 2 minus 1 1 by 2 multiplied by x1 x2 x3, and u is absent here. So this is the state model. This one is x dot is equal to ax plus bu, and this one is y is equal to cx. Right? One more example. One more example. We have ys over us is like this: 2s square plus 8s plus 7 divided by s plus 2 square plus s plus 1, and sorry, multiplied by s plus 1. After partial fraction we will get ys over us, which is equal to 1 by s plus 2 square plus 1 by s plus 2 plus 1 by s plus 1. And if I draw its block diagram, we have integrator. Here we have x1, here x1 dot, and from this x1 feedback of minus 1 is there, and it is added here. Then another integrator. Here we have x2 and here x2 dot. From here I have a gain feedback of minus 2 and it is added here. Okay. Here we have square of this term. So if I multiply this with this term only, means like this. If I have another integrator like this, here we have state x3, here we have x3 dot, and from this x3 here minus 2, and it is added here like this, right? So this term is multiplied with this term to give the square of this term, means we have this here. These two are added together like this, and the resultant is added here. And finally we get ys, and input is shorted. Yes, this is block diagram. This is the block diagram. Here ys is equal to x1 plus x2 plus x3. x1 dot is equal to minus x1 plus u. x2 dot is equal to minus 2x2 plus u. x3 dot is equal to minus 2x3 plus x2. So in the matrix form we can write it as x1 dot, x2 dot, x3 dot is equal to here minus 1 0 0 0 minus 2 0 0 1 minus 2 multiplied by x1 x2 x3 plus input 1 1 0 u. So this is x dot is equal to ax plus bu, and y is equal to 1 1 1 x1 x2 x3. So y is equal to cx. This is the state. Okay, now come to next topic, and the next topic is solution of state equation. Solution of state equation. Solution of state equation. We have a state equation like x dot is equal to ax plus bu, or it is dx over dt is equal to ax plus bu, right? And if I consider all initial conditions are 0 for transfer function, all initial conditions are 0, then Laplace of dx over dt becomes s axis. S axis. And if we have initial conditions x naught when input is absent, means u is equal to 0, then L dx over dt, this will be s xs minus x, right? And when we have initial conditions, means initial vector x naught, but input is absent, the differential equation becomes homogeneous. When input is 0, the differential equation becomes dx over dt or x dot is equal to ax. This is homogeneous equation. So first we will discuss homogeneous equation. Solution of homogeneous equation. First we will discuss solution of homogeneous equation, and from homogeneous equation we have dx over dt is equal to ax. And after taking Laplace, transform, we have s xs minus x naught is equal to a xs, or s minus a xs is equal to x naught, or xs is equal to s, if a is matrix, then si minus a inverse x naught. Si minus a inverse x naught, and if it's considered as an element a, then xs is written as 1 over s minus a x naught. And if I take inverse Laplace of xs, means L inverse of xs, this gives e raised to at x naught, e raised to at x naught xt, right? So this is the solution of homogeneous equation. From here also, if I take inverse Laplace, then xt becomes e raised this L inverse of si minus a inverse x naught. And what is this? This is e raised to at. One expression we have xt is equal to e raised to at x naught, and one expression we have is xt is equal to L inverse of si minus a inverse x naught. It means e raised to at is equal to L inverse of Si minus A inverse. And if I say phi s is equal to Si minus A inverse, then e raised to at will be L inverse phi s or phi t. And this phi t is called state transition matrix. State transition matrix, right? This phi t is called state transition matrix. Clear? So, for finding state transition matrix, we have two options. One, we can obtain this from here, and second, we can obtain this from here. या तो हम इस phi t को यहां से कैलकुलेट कर सकते हैं, या हम इसको यहां से कैलकुलेट कर सकते हैं. जहां से भी इजी हो हम उस phi t को कैलकुलेट कर सकते हैं. तो यह है होमोजीनियस इक्वेशन का सॉल्यूशन. होमोजीनियस इक्वेशन का सॉल्यूशन क्या बनेगा? xt इज इक्वल टू e रेज टू at phi t. And this phi s is called resolvent matrix. This phi s is called resolvent matrix, right? So the solution of homogeneous equation, that is when u is equal to 0, means input is equal to 0, xt is equal to e raised to at x naught, or xt is equal to phi t x naught, right? Next is solution of non-homogeneous इक्वेशन. अच्छा, होमोजीनियस कब है? जब u 0 है. और नॉन होमोजीनियस कब है? जब u नॉट इक्वल टू 0 है. मीन्स व्हेन इनपुट इज नॉट इक्वल टू 0, then the equation is called non-homogeneous equation. And in this case, when we have non-homogeneous equation, like x dot is equal to ax plus bu, or dx over dt is equal to ax plus bu. Now take Laplace transform. We have sxs minus x naught is equal to axs plus bus, or s minus a xs is equal to x naught plus bus. Or this can be written as, since A is a matrix, Si minus A xs is equal to x naught plus bus. Or xs is equal to Si minus A inverse x naught plus Si minus A inverse B US. First expression. And after taking Laplace, inverse Laplace, we get xt is equal to, this is phi t x naught plus, since here we have multiplication of two terms, two frequency terms, so 0 to t, this one is phi t, so phi t minus tau b u tau theta. T minus tau b u tau theta. Right? This is the solution of non-homogeneous equation. Solution of non-homogeneous equation. Right? Now, properties of state transition matrix. Properties of state transition matrix. First, phi naught is equal to e raised to at है ना, तो t 0 कर दिया, this is equal to 1 और identity matrix. Second, phi t is equal to e raised to at is equal to e raised to minus at inverse or is equal to phi minus t inverse. Right? Third is phi inverse t is equal to phi minus t. Fourth, phi t1 plus t2 is equal to e raised to a t1 plus t2 is equal to e raised to a t1 e raised to a t2 or phi t1 phi t2 or phi t2 phi t1. Next property, phi t power n is equal to phi nt. And last, sixth one, phi t2 minus t1 multiplied by phi t1 minus t naught is equal to phi t2 minus t naught is equal to phi t1 minus t naught multiplied by phi t2 minus t1. So this is the properties of state transition matrix. In the next class, we will see the methods to determine state transition matrix and some examples related to calculation of state transition matrix. Thank you.